Welcome back, everyone. In this lecture, we're going to study resistance and Ohm's law, and we're going to see things from a practical perspective as well as analyze the most important equations in this field. So let me start by giving you a kind of a funny circuit that you can build very, very quickly and understand as well as literally feel the impact of Ohm's law. So let's suppose that you pick up a battery. In this particular case, I am assuming you're picking up a 9-volt battery, and you go ahead and you touch the battery to your tongue. You touch the battery to your tongue such that current can flow from one end of the battery to the other end of the battery through your tongue. Now, I'm not suggesting you actually do that. This is more of a thought experiment. It's not like it will hurt you or anything like this, but you know, most batteries are not very clean. Plus, you probably won't like the sensation of feeling a little bit of current flowing through your tongue. But if you take this pretty simple circuit and you try to model it with the schematics we have been learning, you probably will be using a symbol for the battery that looks something like this, as well as trying to model your tongue with some type of an electrical symbol. The electrical symbol we're going to use is shown right here. And I would say this is a pretty good approximation. It's not, of course, capturing everything that your tongue is doing to impede the current flow, but certainly it basically captures the effect that current cannot flow freely from one end of the battery to the other. In other words, you don't really have a short circuit from the positive node of the battery to the negative node of the battery. You have something else which will restrict how much current flows. That something else is what we will call resistance or resistor. So essentially, as the name says, this is a device. It's a symbol, rather, of a device whose main point is to provide some resistance to the current flow. In other words, it impedes the flow of current through it. Now, it turns out that the amount of current that can flow through this resistor is essentially proportional to the amount of voltage that you apply across it. If you were to double the amount of voltage, then you would basically end up with precisely the double the amount of current. In other words, this is a linear element. It's a linear resistor, and every ideal resistor is practically a linear device. Now, this rate of proportionality that links the voltage V to the current I is essentially called resistance, and it has the symbol of R. And that expression that I wrote here, V is equal IR, in most people's minds has a name, and it's basically called Ohm's law. And that's because Mr. Ohm actually studied this law experimentally. So he was trying a bunch of different resistors, he was trying different voltages and currents, and he essentially found out that for simple resistances that follow this ideal linearity relationship, you can essentially write down V is equal to IR. However, I want to emphasize here that V is equal to IR is only half of Ohm's law, even though this is what sticks to most people's minds. The second half of Ohm's law is that this relationship is correct provided that you have defined the voltage V and the current I in the passive sign convention. And that's important because if this is not true, if the passive sign convention is not true in your circuit, V does not equal to IR. So let me put two different scenarios here so you can understand that. So if you basically have a resistance R and you apply a potential difference V, then clearly there will be some type of current I that will flow through this resistance, but I will flow from the positive node of the resistor to the negative node of the resistor. That's the passive sign convention. So if you have basically written down the current I such that the direction of the current goes from plus to minus, then indeed you can write the equation V is equal to IR. On the other hand, if you take exactly the same example, so the same resistance, but now you apply a voltage difference that is the opposite polarity of what you had before, clearly the current will reverse polarity. But if, let's say, you still insist on writing the current I to flow now from negative to plus, that's the active sign convention, then what you will end up is that V should be equal to negative IR. So instead of saying all of this long story, if this then that, then it's much better to simply say that Ohm's law says that V is equal to IR, provided that you're talking about the passive sign convention. So I would really like to invite you to learn Ohm's law correctly from the very beginning, so you don't end up later on in your life getting confused and doubting whether you learned something correctly or not. So once again, V is equal to IR, provided you have the passive sign convention in your circuit. Now, that resistance that I basically used before to model my tongue, or anybody else's tongue for that matter, is essentially a model that applies to many different devices. So it applies, for example, to the conductor that we have used before, shown here. And in this conductor, as we have discussed before, you have a bunch of free electrons that normally move very randomly if you don't apply a voltage across the conductor. But if you do end up applying a voltage across a conductor, then this random motion stops and the electrons flow on average from right to left, which of course means that you have a current I that flows from the right from the left to right. And based on what we just learned right now, the current I should be equal to the voltage that you apply divided by the resistance of this conductor. Now you might ask the question, where does this resistance come from? What influences this resistance? There are many physical laws that will actually govern this. Essentially, that resistance is controlled by the amount of scattering that those electrons will suffer. I want to remind you that the arrows that you see here are only expressing an average motion, an average speed of the electrons from right to left, but the real flow of electron is far, far more complicated than this. An electron, for example, will get scattered when it hits an ion inside the conductor. This is not an empty space. There are actually ions that will collide with those electrons. The electrons will also collide with themselves, and therefore you will have another scattering mechanism. And in reality, those scattering mechanisms are accurately described by quantum mechanics, which is not the focus of this course. So rather than going through all of these relatively complex equations and talking about quantum mechanical flow of current, for large systems, and by large I mean that when they are large compared to a single electron, we can essentially capture all of that topic through all of these effects through the concept of resistivity. So every single material can be characterized by the resistivity, by its resistivity, which is measured in the units of ohms meters. Essentially, this is a number that tells you how easily current can flow for a given amount of voltage. So copper, for example, has some very, very low resistivity because it's a very good conductor, meaning current can flow very easily through copper. On the other hand, silicon is a much worse conductor, and in fact, later on, we're going to say that this looks like a semiconductor. It's somewhere in between a conductor and an insulator. While other materials, for example, rubber, has so high resistivity that it's practically an insulator, which means that if you apply a voltage, no matter how much voltage you apply, you practically will get almost no current flow through it, or negligible current flow. So keep in mind that every material has its own resistivity, but in addition to choosing the material, we can also choose the dimensions or the shape of the conductor. In this case, I'm giving you a very simple example of where I have a cylindrical conductor with some length L and some cross-sectional area that you see here, A. So for this particular case, there is an equation that will give you the resistance of this device. So the resistance of this device will be equal to rho, which is essentially the resistivity of this material, times L, which is the length of this cylinder, divided by A, which is the cross-sectional area. So I will not go ahead and prove this equation. In more advanced courses or in physics courses, you can easily find this proof. But the point I want to make sure that you understand here is that not only it's important to control to choose the material with the right resistivity, which is shown right here, but also you have the flexibility of choosing the right length or the right cross-sectional area such that eventually you can get the resistance that you want. Of course, this equation is true only for the cylindrical conductor. You can find many different shapes and essentially get similar equations for resistance. So what I would really like you to remember here is that resistivity is a material property. On the other hand, the absolute resistance measured in ohms is not just a material property, it depends on geometry as well. Now, in real life, you will never go to a store and ask for a resistor that will look with this zigzag pattern here. Those type of things really don't exist. Resistances can come in all kinds of shapes and patterns. In this graph, in this slide, you can see two different images that represent, I would say, very common resistors. So these are resistors here on my left where you can find easily on a circuit board. And these are essentially some variable resistors with a little trimmer there that you can use, essentially a screw, to control how high or low or how low of a resistor you can build. There are some codes here. If you look, for example, at these colors, those are essentially codes that can tell you what is the value of this resistor just by just looking at those colors. You can easily find books or things online that will help you understand how to interpret this code and how you can read the value of the resistance in ohms when you see that. Lastly, on this slide, I want to emphasize that even though the image here on the left shows the most common value, the most common symbol for resistance, you will find other symbols, like, for example, the one here in books or in the literature. But typically, as long as you see the letter R on top of those, you can easily understand that we're talking about an ideal linear resistor. Now, in addition to defining resistance, we often define the concept of a conductance. And let me give you immediately the equation for that. So conductance G is nothing else but 1 over R, where R is nothing else but the resistance that you just learned about. R is measured in ohms, while the conductance is measured in Siemens. And of course, Siemens is 1 over ohms, is exactly the opposite. Now, some people like using resistance. That's really the more, I would say, common way of introducing resistors. Some others, or in some particular cases, we will be using the concept of a conductance G, and all you really have to remember is that G is equal to 1 over R. Now, in real life, everything has a finite resistance. Even the most pure conductor will never give you a zero resistance, or the best possible insulator will never give you infinite resistance. But in typical scenarios, once a resistance is above a threshold or below a threshold, can be easily considered or rather approximated by an open or a short circuit, like what we have learned so far. So if you see a circuit where it simply says that R is approximately infinity, it means that for all practical purposes, you can ignore that resistance and replace it with an open, with a break. Similarly, if you see a resistance indicated as 0 or approximately 0 in a circuit schematic, it practically means that you are dealing with a short. Now, when you have an open, clearly there should be no current flow, which means that I in the loop where the open is contained will essentially be equal to 0 amps. And in a very similar way, if you have a short, then the current will theoretically be infinite. And you might want to go back to the video that we talked about shorts and open circuits, and you will find out that shorts can be quite dangerous precisely because of the fact that they result in very, very large currents, theoretically infinitely high. The very similar things can be stated from the point of view of a conductance. So when your conductance is basically equal to 0, means nothing is being conducted. Essentially, you have an open where your conductance is infinite. It means that there is basically 0 resistance to current, and therefore you have a short circuit. So this is the last slide for this lecture. I want to thank you for staying with me, and this is the first introduction to Ohm's law and resistance. Thank you very much.